Okay, so yeah, let's talk quadratics. So I want to just define a couple things real quick. And I know you guys have talked a lot about quadratics back in Algebra 1, but it's been a little while. For now, we're just going to define a quadratic function like this. Later on, we'll define it a little differently. We'll define it as a type of polynomial, but we haven't talked about polynomials yet. So this is what we're going to say now. A quadratic function is just a function that could be written in this form, right? Where a and b and c are real numbers, and the only thing that has to be true is that a can't be 0 if it's going to be quadratic, because quadratic implies that it has an x squared in it, okay? But the other, b and c, could both be 0, for example. Quadratic equation, which is what we're going to really deal with, is solving quadratic equations. We're going to start to kind of talk about strategies for that. Is one that we could say could be written in the form ax squared plus bx plus c equals 0. And once again, the only real constraint here is just that a, b, and c are real numbers, but a can't equal 0. Okay. So let's kind of just look at a couple of these, and you tell me what you think we could do to solve this equation. So how about something like, well, think about that for a second. Ideas. What do you think? Yes.
Bring all the values on the one side.
Okay. So we're going to put it into what we call standard form. Standard form is where we set it equal to 0, right? Okay. That's a good idea. We'll talk about why here in a second. So we're going to push everything to the left. We're going to put it on the side where we have a positive number of x squareds. How about? So, and that's a good idea, by the way. We'll talk more about that later. When you're solving quadratics, I'll say it now and I'll repeat it many, many times, but you really want to have the coefficient of x squared be positive. Okay, and that'll go for, you'll see a ton of reasons why that's the case, but just it's a good habit to get in. So we're going to add 4x to both sides and add 6. We get something like that. Does everybody agree?
Yep.
Okay. So this is different than the kinds of equations that we've solved so far this year, right? The kinds of equations we've solved so far this year have been pretty easy. They've been the kind where there was a single x value up there and finish the statement. If you can point to a single x, then you can isolate it, right, by reversing order of operations, right? This is different though. This is different because now we've got two different x terms and they're not like terms, and so I can't combine them, at least at the moment. We'll learn some tricks how we maybe could combine them and form a single x on one side of the equation. But for now, we don't know those tricks. So what are we going to do? What do you think? Remember? Remember what we do, Sam? No idea?
Don't you have to find two numbers that add up to 4?
Okay, but you're right. So you're gonna try to factor it, right? Why? What's our motivation for doing that? What do you think?
Because you can find two x values that work.
True, but once again, you know the pattern and you know how to do it. But I want to know what's the motivation. Why do we do it? Because I think that's an important part of math, is knowing strategies. Why are we doing this?
The x-intercepts, if you were to graph it.
Okay, that's related to what I'm looking for. Yeah. We're trying to find all the values of x that satisfy that equation, right? When it's written like this, that's a pretty tall order. This, because this one happens to be an easy one, you probably could just, by trial and error, find the values that work, because they're integers. Okay? But you can pretty easily see that there's going to be a point where maybe that's not going to be the case, right? Where it's going to be harder to find answers. What if they were real numbers that were, irrational or something? That'd be really tough to do. Yeah.
Quadratic formula.
Then we could, at that point, use the quadratic formula. But let's not do that for now. Let's talk about why is it that we would factor this. If I want to try to find values of x that simultaneously make the sum of these three terms go to 0, that's a hard thing to consider, right? That's hard to find values that are going to make that work. There's really no good trick for finding values that make three things add to 0. But if I factor this, tell me why this is a much better form to write this in. And what is it going to factor into? Remind me how we do this factoring business.
X plus 2, x plus 2.
Okay, how'd you get that?
Because 2 times 0 multiplies to 4 and adds up to.
Okay, good. So whenever we have a coefficient of 1, we know that I'm essentially just unfoiling this, aren't I? So we know that first times first has to multiply to x squared. So those are both x's, right? We just need to find the numbers that work so that when we FOIL this out or expand it, we get this answer. And the trick is we've got to find two numbers that multiply to the constant and add to the coefficient of x, right? In this case, we get that, right? Okay, so let me pull up just for a second another example so you can stare at both of these and tell me why this is such a good idea. So what if we had something like this? What if we had, I'll put it in standard form for you. What if we had x squared minus 3x minus 10 equals 0? What's that going to factor into? What's that factor into? What are my numbers going to be this time? Multiply to negative 10 and add to negative 3. Negative 5 positive 2. Okay, why is it so much easier to solve for the values of x that make this true than it is the ones that make this true? What do you think?
You won't have to make one of the values equals 0, because anything 0 equals 0.
Oh, okay, yeah. Yeah, it's a lot easier because things that multiply to 0, that's pretty easy, right? We know, what's the only way that you can get a product to equal 0? If one of the factors is 0, right? That's called the zero product property. So it's a pretty good idea, right? If we can factor this thing, we can say, okay, the only way that the product of this factor and this factor equals 0 is when this factor equals 0 or that factor equals 0, right? And so then we know what the solutions would have to be. One of them is going to be the solution to the equation x minus 5 equals 0, and the other one's going to be the solution to the equation x plus 2 equals 0. So we just get x equals 5 or x equals negative 2, right? Okay, does that make sense? So factoring, is it a good plan? A good strategy? Sure, if it's easy, right? What do you think potentially the shortcomings of trying to solve a quadratic equation by factoring would be? Because really, we want to start looking at this. I really don't. I like to look at math as kind of a tool. We want to be able to solve an equation, but we want to do it in the best way. And we're going to come up with a whole bunch of ways we could deal with quadratic equations. And part of what I want you to know is how to start with one and analyze what's going to be based on what I'm given, what's the best strategy. Right? Solving by factoring is certainly a valid and good strategy under certain cases, but when would it be not good?
When the coefficients are really big.
Yeah, if it was really a hard quadratic factor, why would you go through the hassle if we're going to have a reliable other method that wouldn't be as difficult, right? And so really it's only something that's going to make sense if it's easy to do. In real life, oftentimes when we're dealing with quadratics, the numbers, the coefficients aren't even necessarily integers. They might be decimals, or they might be square roots or something like that, right? And so this only makes sense if it's an easy pattern to see and easy to factor. I would even say that if you have a coefficient of x, I know you guys learned how to do this, and we could review it today, but I don't even think I will. I mean, at some point I'll plug it in. But how do you factor if a is not equal to 1? Did you learn bottoms up?
Yeah.
Okay, you did learn bottoms up. Okay, and I'll review that. It's good to know, but you'll almost never do it, because why would you? You could just use, for example, the quadratic formula, right, which we'll review that soon, I know you've learned that. So you never will, right? Okay, but if we've got, so let's kind of break this down to a strategy then. If we've got a quadratic equation that involves both x squareds and x's, for today, our best and only strategy that we're going to talk about is factoring. We'll add some other stuff later. But what about some other kinds of quadratics? What if we had something like, let's say, what about this? What if we had x squared plus 4 equals -5? I would say that's a much, much easier equation to solve. Looks easier. Why might you say, yeah, that's a lot easier because what? What's going on?
You can just subtract
A1
one.
squared.
Say it again.
You can just subtract 1 to the square root.
Okay, yeah, there's a single x there, isn't there, in this case? So I can go back to just reversing order of operations here, right? First I've got to maybe, well, do I want to set this one equal to 0?
No.
Not really, do I? This is a little different strategy, isn't it? In the previous ones, we were trying to set them equal to 0 because we wanted to be able to factor them and use the zero product property, right? Now I could, by the way, I could do that here, right? I could add 5 to both sides. Actually, no, I couldn't. That's not going to be any good. Let me change. That's a bad problem. Let me change. We'll do that one in a little bit, but I don't want to do that one quite yet. What if we had something like this? X minus 4 equals 5. How about it? I could subtract 5 from both sides and get x squared minus 9 equals 0. And I could factor that. Remember how to factor that?
3. Don't I just pretend that there's like a 0 x?
You could. Yeah, you could pretend there's a 0. So what Katie's saying, and this is a good idea, you could pretend that there's a 0x in the middle and just look for numbers that multiply to -9 and add to 0. What would those be? Plus 3 and minus 3. Good. Or you could also think about this as being x squared minus 3 squared, and that's a difference of squares pattern. Do you remember the difference? And we'll hit all this stuff at some point. Do you remember what that pattern's always equal to? This is kind of an important one.
AB squared?
No? This is a difference of squares, and sometimes it's called a conjugate factor pattern, where it's a plus b times a minus b. In math, these are what we call conjugates, where they have the same terms but different sign in between. The sum times the difference is a conjugate, okay? And that'll come up a lot. Comes up a lot all the way through calculus. We kind of take advantage of that pattern a lot. But those are all, we could factor this, but maybe there's an easier and better way. Go back to that same problem. X squared plus, what was it? No, minus 4 equals 5. Because we can point to a single x, we can isolate it, right? And all we have to do is just reverse order of operations. So if we follow the rules to reversing order of operations, what are the steps in order we do to get x by itself?
Subtract 4.
Okay, we're going
Or
to add 4. Okay, we got to add or subtract. So x squared equals 9. Is there any multiplication to deal with?
No.
No. Exponents.
Yes.
Yeah, there's where the exponents come in, right? What would I do next? How do I undo squaring something?
Square root.
Square root. Okay, so then I'm going to get x equals what? Square root of 9. I'm missing something though. Plus or minus, right? Remember that plus or minus. And remember where that comes from. Right now, maybe it makes more sense. We've talked about absolute values. If I take the square root of both sides, remember we said the square root of x squared is what?
The absolute value.
Absolute value of x. And if the absolute value of x equals 3, now we know what is x equal? plus or minus 3, right? Yeah, we've talked about that, okay? So that's where we get the x equals plus or minus 3 answer, right? Okay, so, whoops. Okay, so let's look at something maybe a little different. How about something like this? What if we have, it's a little bit harder. What if we have 2x squared minus 1 equals 23? Okay, what are the steps in order to get x by itself there? First I add 1, then I divide by 2. What's that? Oh, we just kind of chat wherever today. Then divide by 2, and then square root. Okay, so if we do all that stuff, what are we going to get? 2x squared equals 24. Would you agree we end up with x squared equals 12?
Yes.
Okay, so if I square root both sides, I get x equals plus or minus square root of 12, but that's not simplified. Okay, what do we do to simplify that? In this case, 12 is not a perfect square. What can we do?
Separate it to like square root of 3.
Okay, good. We're going to take advantage of a property of exponents, or property of root, same thing. So we've got this property that says I can take the square root of a product and write it as the product of the square roots, right? And the reason we're doing that is our goal is, and here's how you think of it, our goal is always to get as much of the number inside, we want to pare that down as far as we can. We want to get as much of the number outside of the radical as possible. So then what we're looking for is just the biggest perfect square that divides evenly into 12, which in this case would be 4, right? And so we'll write this as plus or minus the square root of 4. There's my perfect square times the square root of 3, right? And that gives us plus or minus 2 times the square root of 3. Okay, and that's our simplified answer. Okay? Good. What about something like, what about something like this? How about if we got 2 times the quantity 3x plus 1 squared minus 7 equals 4. Okay, a lot going on there. What do you think? What's going to be what's the first thing I'm going to do there? Kristen, what do you think? First thing? Add 7. Okay, so first thing, we'll add 7 to both sides, and we'll end up with 2 times the quantity 3x plus 1 squared equals 11. Okay, what's next? Divide by 2. So we get the quantity 3x plus 1 squared equals 11 halves. Okay, now what? Okay, yeah, if we follow order of operations, look what we've done. We took care of undoing the addition or subtraction first, right? Then we took care of undoing multiplication, right? Next level up would be exponents, right? So we've got to undo that exponent. Okay, so what's that going to look like then? What am I going to get on this side?
3x plus 1.
Equals, okay, square root of 11 halves. I thought I heard plus or minus. You've got to have a plus or minus, right? Whenever we take an even root, for now a square root, of both sides, we have to have that plus or minus in there, right? Okay, so we're not done though, so now what? Subtract 1. Okay, now I got a trick for you here. When you subtract 1, the natural thing to do would be to subtract 1 at the end. Anybody have maybe a better idea? Put it in front. Yeah, put the negative 1 in front, right? So we end up with 3x equals -1 plus or minus the square root of 11 halves. Okay, make sense? And then last step, divide by 3. Okay. But that doesn't look very simplified, does it? Okay, we gotta probably do some stuff to that. Okay, so what are we gonna do to simplify that? Well, first of all, let's just focus for a second on that. Right? How do we simplify a radical like that? Do you remember talking about that? No, for one?
You have to multiply by a fraction equal to 1. You use like the
Yeah.
denominator, so root 2 over root 2.
Okay, good. So yeah, if we take the square root of 11 halves, first let's write it as, we'll use the product that says if I have the quotient of, or the square root of a quotient, that's equal to the quotient of the square roots. I can split top and bottom, right? So square root of 11 over square root of 2. Neither one of those would be, I couldn't simplify either one, could I? There's no perfect square that divides into either one. I would if I could, though. That would be the next step. But I got to get that radical off the bottom. That's called rationalizing the denominator. Right? We don't want that square root in the bottom. So we're just going to multiply top and bottom through by the square root of 2. How come?
It'll get you a perfect root on the top.
Yeah, good. And there's a couple ways to think about that. The square root of 2 times the square root of 2 is what? The square root of 4, which is a perfect square. And so that gives us 2. Another way to think about that would be, what's another way of saying something times itself? What is that? Like if I have x times x, I would say x squared. So the square root of 2 times the square root of 2, we could write as the square root of 2 squared. And the square root, a square root and a squared, right? I say we had f of x equals the square root of x and g of x equals x squared. Those are inverses, aren't they? They undo each other, right? And so they cancel each other out. And I end up with 2 either way, right? Just totally separate but compatible ways of thinking about that. Either way, though, what we end up with is x equals -1 plus or minus. On the top I'd get, what would I get on the top, by the way? We never, what's that? Yeah, square root of 22. And 22 is not, there's no perfect square factor of that, right? So we have to just leave it as the square root of 22 over 2. Now what about this dividing by 3 stuff? Talk to me about how are we going to deal with that? I've got that whole thing over 3. That's not simplified. It's not simplified if I've got a fraction of fractions. What could I do? There's a bunch of ways I could go about this. We're kind of getting to that point in math where a lot of what we do is we just see how 2 things are the same. What could I do?
By the opposite.
By the reciprocal. Good. Okay, so I could write the bottom as a fraction, and dividing by a fraction is the same as multiplying by the reciprocal. That's a good way to do it. So then this would equal -1 plus or minus the square root of 22 halves times 1/3. Now, that's a really good way to do this. What must I do, though? If I'm going to multiply this by 1/3, what should I do here to the numerator? Parentheses. Everybody see that? Because if I'm going to multiply by 1/3, if I don't include parentheses, it looks like that 1/3 is just being multiplied by 1 term. Okay, even if in your mind this is just scratch paper, and you think, well, I know what I'm doing. Don't do that. Don't do that. It's a really bad habit to get in math, and I'm not sure, well, a couple things I'm going to do to address that. So one thing is I want you starting now, I've been really bad about this, but starting with this new unit, I want you to be writing down everything in your notebook, and I am going to check routinely. And what I want to be able to do is I don't expect it to be, look at my desk. I don't expect it to be extremely super well organized. But what I want to be able to do is, I want you to be able to find the work to a given assignment. So just like know that, scratch out this is assignment 3.1.1, and then your work can just label the problems. It can be out of order, but I want to be able to say, okay, show me, this is how I'm going to give you a grade. Show me your work to, I'll randomly pick an assignment, this assignment. You got to be able to show it to me. Okay? Doesn't have to be super organized, but you got to be able to find it. Okay? And there's a couple reasons for that. As I've said before, probably the most important one is I want to be able, if you've got questions, from now on, I got to do a better job of this. I'm not going to answer any questions because we're getting into more algebraic algebra now. I want to see your work. I don't want to just sit down and go through a problem until I see what you have tried first, and that's in the form of work. Okay. The other thing is being able to organize algebra is really important. Look at my calculus class, and I bet you 80% of what we do in calculus is just algebra, right? And it's hard algebra, and you got to be organized or you're done, right? So you have to develop those habits. Okay, so now what do we do? Last step. I mean, maybe that's okay. If we want to go one step further, probably should go one step further. Yeah, distribute it. So if I distribute the 1/3, what do I get?
Negative
Plus or minus square root 22 over 6, because I just multiply fractions straight across, right? Everybody see that? Any questions? Okay. All right. What if I've got, excuse me, what if I've got something like this? Let's try another one here. What if I've got something like, the first one I gave you, x squared minus 5, plus 5 equals negative 4. Okay, what about that? Okay, because what's my strategy going to be here?
Check both sides.
Okay, but if you had to articulate a strategy, we're not factoring, we're what?
isolating.
Isolating x, right? Okay, because I can point to a single x. So we'll push everything away from the x, subtract 5. I get x squared equals negative 9, and now if I square root both sides, I get x equals plus or minus the square root of negative 9. Okay, sometimes we might say we're done. If we're looking for only real answers, we're not going to find any, are we? Right? That's one of our 2 rules of real numbers is I can't divide by 0 and I can't take an even root of a negative number, right? However, there are answers here. They're just not real answers. You've talked about this before. What do we call these kinds of answers? Yeah, they're imaginary. I'm going to take advantage of that same property of exponents that we looked at earlier. The square root of a times b equals the square root of a times the square root of b. Only this time I'm going to break it up into plus or minus the square root of 9 times the square root of negative 1. What's the square root of negative 1? Yeah, the square root of negative 1 is equal to I, which is the imaginary unit. Okay? By the way, imaginary is a horribly unfortunate name for this because it sort of gives the impression that somehow these things, well, I mean, compare the two number sets we talk about. Real numbers and imaginary numbers. Which one sounds like it's kind of fluffy and which one sounds like it's important? I mean, the real one sounds, yeah, we want the real one, right? We don't care about this imaginary stuff. That's a really bad and unfortunate title for this because imaginary numbers are every bit as real numbers and every bit as meaningful. They just do different things. Real numbers are primarily associated with cardinality. They're going to count things, right? But imaginary numbers do something equally important. Imaginary, like for example, when I studied physics in college, I would bet probably at least half of the analysis I did in physics involved imaginary numbers because they are a real part of physics. I mean, if you want to, for example, if you want to calculate the overall impedance of a circuit or something, the impedances are going to be, of the different components, are going to be imaginary numbers. You know, and that's something that might sound like a bunch of mumbo jumbo right now, but that's a big part of electricity and magnetism. I mean, that's something, if you go into electrical engineering, that's what you're going to do, a lot of that stuff. In optics, if you want to calculate focal lengths of compound lenses, once again, you're dealing with imaginary numbers, you know, complex numbers with imaginary parts. There's a lot of this kind of stuff you can do. I remember doing, this is kind of interesting, I remember doing a problem where, and I just because I want you to, I mean, this is kind of fun. So if you want to do something like this, let's say we've got this pipe. We've got this pipe that rounds a corner, and we want to predict what the velocity of the water is going to be at some point down the pipe somewhere, okay, after the bend. That's hard to do. It's hard to do because when the water goes through the bend, it undergoes some mixing, right? You can think of the flow of the water as being laminar, meaning think of it as flowing in layers. So where do you think the water is going to flow the fastest in a pipe?
On the outside edge.
On the outside edge? I'd say it might flow the slowest on the outside edge. How come?
Longest distance.
No, there's something else going on. Why would the water going along the edge of the pipe flow the slowest?
Most friction?
Friction. Yeah. It's going to have some friction with the side of the pipe, right? And so if you think of it as a bunch of concentric layers, like when you recycle, you know how you put the cans, you nest the cans inside each other, right? So you got the layer of water on the outside of the pipe, and then there's one inside that, there's another layer, and then there's another layer. Well, think about this. The slowest layer has got to be the one on the outside because it's touching the stationary pipe, right? The next layer of water is going to be slowed down by the outside layer a little bit, et cetera, et cetera, et cetera. And so it's like the lead of the pencil in the middle, that's going to be where it goes the fastest, right? Make sense? But the water has momentum. The faster it goes, the more momentum it has. And so when it goes around the bend, this bit of water in the middle, its extra momentum carries it a little further down, and so you get some mixing in there, right? And it makes things really complicated, right? But if you do some what's called a conformal mapping, and you take this pipe and you use complex numbers and you project it into the complex plane and you make the pipe straight in that mapping, then you can take advantage of the fact that it's pretty simple flow in that orientation. You can answer the question, okay, if the pipe was straight, what would be the value of the speed right there? And then you just map it back into the real plane, and you get an answer. That's pretty good math, right? So once again, just kind of a little example of why, even though this is an imaginary number, it's really not, it's not. I mean, that's a bad name. It's just a different kind of number. It's just as valuable. Yes?
Wait, so if you found out the speed of the water, if it was straight, and you just mapped it up there, wouldn't it be different?
It would, right. But the thing you're doing is I guess I should have waited a couple days to give that example, because it's using what's called the complex plane in a mapping where you're going to say, you're going to map some parts of that system, you're going to map into a different plane. So in that plane, the pipe is straight. It makes certain things more complicated, but the difference is much less significant than it would be if you actually tried to just take the pipe and bend around the corner. That's a pretty bad description, but just the idea is by harnessing the power of complex numbers, you can make that a much easier problem to solve. Okay, so they're imaginary, for now, imaginary numbers, right? Imaginary numbers are just bad name. Okay, so then what do we end up with? Go back to our example here. So after that, my digression. We end up with plus or minus, the square root of 9 is 3, and this is what we call I, right? So this is really a pretty simple thing to deal with. We don't have to go through that step every time. We just know that if I'm taking the square root of a negative number, what do I end up doing? What happens to that minus sign inside the radical? It turns into an I outside the radical, right? Everybody get that? Okay. And so really in terms of the algebra, it makes it really no more difficult, right? Okay. let's do one
Just
more.
minus 3 is it plus or minus?
Say it again.
Is it just minus 3i?
Oh, no, it's plus or minus, you're right. Plus or minus. This part goes to there, and the negative sign just becomes an I that we tack on, okay? Let's try just a couple more of those. I just want to point out a couple little things. So what if we had x squared equals the square root of negative 72? What are we going to get? How am I going to deal with that? Tell me some things I'm going to have to do to that. Okay, good. So for one thing, we know that we're going to get an I out of that, right? What about the square root of 72? Okay, 36 and 2, isn't it? So the square root of 36 is times radical 2 then, right? So where does the I go? Tell me what's wrong with this picture. It's okay, but what's potentially the problem with that? It's okay. This isn't that big a deal. But in math, what do you think?
I might look like it's under the square root.
Yeah. You see like where we end a radical, there's always a little bit of ambiguity if we're writing this, right? Because you might think, okay, is that I, did they really mean to put the radical over there? Because we could have an I inside a square root, or not. And so where do we want to put, so we always like to put stuff if we're uncluttering all of our factors, right? And we're stacking them in an order. We always like to stack them so the radical goes last. So where do you think we might put the I? After the 6. Yeah. You see that? This is not a hard, fast rule, but you kind of see where that stuff comes in. Okay. All right. So let's take an example. Let's take this. Let's take the example of, what's this thing called again?
The Burj Khalifa.
Burj Khalifa. Okay. Tallest building in the world. 2,722 feet tall. That's more than half a mile. That's a big building. Okay. I mean,
Think
it's,
of all the stairs you could do in there.
yeah, you could. You could really get in shape.
I mean, compared to
So here's our formula. We've got, let's say that we want to drop a water balloon off the top of this thing. That'd be the ultimate water balloon drop, wouldn't it? Okay, so we're going to drop a water balloon off of this.
break on the outside of the building.
Let's answer a couple questions about that. Let's do a little physics. So this is the formula if we're using feet, which we don't like to do, but if we're using feet and seconds, this is the formula for how long it takes an object, where an object's position is as a function of time. If this is the initial position, initial height, and t is time, right? So let's say we want to know how long does it take for something to hit the ground. What am I going to do? So what would the height at the ground be? 0. So what am I going to plug in 0 for? For that, right? For this is the height as a function of time. We want to find the time it takes to get to a height of 0, right? This is a constant. That's the initial height. So what is that for this building? Yeah, 2722, right? Okay, so then we're going to just solve the equation. 0 equals 2722 minus 16t squared. Okay? That's a lot of what physics is. I mean, it's just taking physical relationships and turning them into, this is how you communicate with the physics gods, is by making an equation, and they'll give you some answers. So what do we do to solve this? Okay, yeah, we could. I'm going to suggest it might be something better. Because we'd like to get, if possible, we'd like to get the coefficient of whatever the quadratic term is positive. Imagine you had an idea. I saw you had an idea there.
Just add the 16.
Yeah, why don't instead, and I think a good thing to do when we do algebra, and we haven't done a lot of it yet, but a lot of times I'll talk about things like pushing variables one side or the other, right? Wouldn't we really just want to push this term over there to make it positive?
Yeah.
So then we'd end up with positive 16t squared equals 2722. Now what are the two steps in order? Divide by 16. What's that give us? 170.125. And then last step, t equals plus or minus the square root of 170.125. And that's going to be about what? Yeah, just barely over 13, isn't it? Yeah. 13 and some change.
That's in seconds.
So roughly 13 seconds for that balloon to hit the ground. How about that for a long time? Which one of those do we probably want, the plus or the minus? The plus. Okay. Think about the minus one. See if you can tell me why the minus one is there. It has some meaning too. What's that?
You want to throw the balloon up?
Exactly. It's how long it would take if you threw it up with the same speed it hit the ground with. That's how long it'd take to get to the top.
Yeah, tap once, hold it on.
Yep.
For the surface area of the balloon causing friction.
Good point. Good point. But we'd spray it with some slip rim.
But you can't completely reduce friction, there'll still be some drag.
Yeah, but you'll learn in physics class. We'll talk about slip rim. You buy it at the Acme store.
Come on, Matthew, that's.
We're actually gonna get to work today?
Yeah.
Oh, there's no test today?
Yeah, test.
Oh, okay.
Test today. Yeah.
We're testing today?
Yeah.
You didn't test last period. You were in what?
Yep. Yeah.
You don't even know about
Morning.